Hurst. I've been with Fluke time, previously Hart Scientific, and been almost 38 years now. We've been designing temperature sources like dry wells, baths, and so forth. And today we'll share some of the experience we've had dry wells. We're going to talk about uncertainties, thermal uncertainties related to dry wells. Now these form of temperature stability, and of course that spans all types of temperature sources, as does temperature uniformity, which for the purposes of this discussion, we're going to break that into axial and radial uniformity. Also, we're going to just block living hysteresis of the control sensor, effects, and how those all relate to an uncertainty budget. A few years ago, a dot from called EA 1013. It's currently G13, and it describes a methodology of testing these various uncertainties and how to evaluate your temperature calibrators. So we'll basically follow along that general concept. What we got is the way that the dry calibrator is used. There's a couple of methods here I'm going to discuss, and first of all, we're going to talk about what I call the direct mode. That has to do with measuring and comparing the unit under test with the actual calibrated temperature sensor that controls the dry well. So that is represented on the display, and, so you can compare then the display with the unit under test, which in this case it's got its own display and readout. The other method is that's the indirect mode. Different now. Oops. Sorry about that. The difference is instead of comparing against the sensor and the controller readout, we'll use an external reference thermometer. So we're comparing right inside Whittle and dry wells is a removable insert, and so the issues we may have with the thermal separation from the and the thermometers that we're testing is improved by not having this gap, air gap, that's around the temperature sensors and around the block there. Item here is temperature stability. What we like to do is have a period of time where we can examine the way the controller and controls operating with data and analyze that in terms of its stability performance. So here you see a sample of data, which is in this case over 30 minutes long, and for a dry well I like to measure 30 minutes and kind of look at that and say, well, what is it doing in terms of stability? Now there's different ways of evaluating that. In this particular case, you may be using something like peak, which is looking at the maximum versus the minimum temperature and looking at that overall spread, or sometimes dividing it by 2 for a plus and minus value. Statistical approach is to use sigma, which is 2 times the standard deviation. Now, you note that that's a different value than what we're getting here. Plus or minus here is kind of a construct to say that we've got a bell curve, and if we're looking at that peak and looking on both sides, it's kind of a plus and minus. So it's similar in a way to this, but 2 is equivalent to 95% of the look at is temperature uniformity. I mentioned we'd break into axial uniformity, which is variation of the temperature along the axis. Along the axis of the insert, movable, or in some cases, just the block itself. So we have a specialized sensor that we measure along the axis to come up with a value for axial uniformity. Now in uniformity, it's done similar fashion, but we're working here from well to well. Typically in a dry well calibrator, you have multiple wells. And for our purposes here, we're going to assume that there are several wells of all the same size, so that when we go from well to well, the fit with the probe that we're going to use is the same. Not the same, then you're going to have apparent uniformity errors that are really just errors due to inadequate fit. They examine what we call the measurement zone, which is basically a predefined zone that includes all the different wells that you're going to use as an axial component. Axial uniformity in the CG13 defines a specific thermometer. The thermometer is defined as having a element length of 5 meters or less in length, and a diameter of less than or 6 millimeters or less, and so that helps reduce apparent to ambient stem conduction. Okay. Secondly, CG13 will define number of steps. Number of steps may be dependent upon your application. The intent is that many thermometers will have a set length of 20 to 40 mils, sometimes a little longer. And what you want to be sure of is that you cover that sensor length. And it's about what the impact is of different sensor lengths in a bit. What is recommended here then is that there's a measurement at the bottom, millimeters up, and then 40, and 60 or more, depending on, again, upon what your application is. Example. Now, we do a gradient. We're actually using 2 probes. For the axial measurement, we're going to use what we call a gradient probe, and that's represented here by this lighter blue line. We also have a reference probe. You can see the darker blue line here is representative of that value. Now, the objective here is to be measuring stability at the same time we're measuring gradients. And what we'll do is, in our spreadsheet, we're going to subtract those 2 values, come up with a temperature difference. You can see here on the right axis, we've got a value starting at 0 and go up and down in value. And for my convenience, I like to normalize this first one to 0. And then direct comparisons then on how quick a view of what those deviations are. You need to let those thermometers rest, dwell at the temperature for a sufficient period of time that you can get some stable data. So I've represented that by circle. So we've got this portion of data which we know is stable, it's finished to making a transition. We know that for each depth measurement. So in this case, we've come up at where I've normalized everything to 0. I've got a period of time here. I get 20 millimeter position. Again, for the 40 millimeter position, you can see that that one took a little longer, so it's a good idea to leave it for a little while. And then at 60 millimeters, you'll notice that these temperatures were increasing and finally dropped. That's really typical. What's going on here is when you take a metal block and you hit it with a more constant watt density from top to bottom, it turns the center is actually the hottest. So at some point, however, it will start to cool off naturally, and there's also a component here of stem conduction, which is going to drop your temperature towards ambient. So here we're at 100 degrees C, more or less. So we're increasing as we approach the center of the block. Then would have probably started coming down, but we've got a little bit of an impact of stem conduction. We'll describe the stem conduction problem in a little bit. It's essentially the process you go through in making a measurement. You evaluate that. Now, in this case, I have plotted the data points for a similar measured, and now I've got to examine what am I going to do with that information. You can see that we've got 32 degrees total error from the very, very bottom. I've normalized it again at 0, so it, it's assuming that that is a 5 millimeter sensor in this case, which is not too likely that you'd have that. It's possible, especially if you're using something like a thermistor, or in cases thermocouls. Nevertheless, quite a bit of error, and you'll find that one of the greatest uncertainties you'll measure is the axial gradient error. Well, how do you accommodate that? An examination of that. Look at what if we were comparing probes, all the same sensor length, all the same general construction. What actual temperature might be some iterated value over that temperature length that would be here, and if you were to measure all of them the same size, it would be pretty similar. If to compare a thermometer of a different dimension, now we've got on here just drew it might look like for a 20 millimeter element. Look at the integrated value over that distance. It comes out here somewhere, whereas if we're looking at the integrated value of the 40 millimeter element, it would be here, and we can see that there would be a theoretical 9 millidegree difference between the two. That's a lot better than 32 milledegrees, but so you can work out further. Now, in a lot of cases, if you were just comparing all the size, you wouldn't really have to worry about this entire thing. What you have to worry about is, well, the variation in the construction of that thermometer. Can that element move up and down a quarter of an inch or something inside that device? You might have to work with some manufacturers to kind of determine that. They're clearly never quite at the bottom. They have to leave some clearance at the bottom, and they can vary depending on how it goes together somewhat. Extreme example, and I'll show you a trick that you can use. That was a fairly high temperature, 600 degrees C, so if there's going to be an axial gradient error, and you should see it at that temperature. And you see that this particular unit that's being tested is pretty severe. We've got a grid, we made a 50 millimeter yeah. It's bad. So what do we do? Is there anything to do with that? We don't have to deal with this 2.6 degrees very much. So again, comparing a 20 millimeter element against 50, and by the way, some of the better reference are in the 40 to 50 millimeter sensor element length. But comparing those two, we've got, looking at the integrated values here, we've got all intents of a degree potential error. Well, something you can try, and we've got a paper online about that, is actually a lot of centers of those two probes. So we just take this 20 millimeter probe, we move it to here now, so its center line is the same as the center line of the reference thermometer. Now compare and it's considerably smaller. So with a very bad axial gradient, then there's still some hope. Uniformity measurements, we're using a different probe for the gradient probe. In this case, we're going to use a probe that is exactly the same as the reference probe. So more typical of what you might expect to use applications. And what it is, we're going to have the reference thermometer in one location, it's stay there at the bottom. Then move the gradient probe, or in this case we'll call it the mover, from one well to the next. Here at Fluke, we've standardized testing uniformity with a hole insert. The 4 holes are all exactly the same size. They all fit the probes that are involved. So as we go from well to well, we've got one filter in the reference holes, so we're measuring 3 of the holes. So again, we're using the 2 thermometers. I'm going to measure the first one, let it come to a stable temperature. You can see this one could have been longer, but it's a noticeably stable level in that of time. Again, we're going to the 2 values, and I get normal on the first one, so I can get a quick view of what the temperature differentials are looking like. And here we've got measurement. We can see that we've got minimum one and a maximum one out of those 3 wells. That represents our error, at least over those 3 wells. Now I wonder, what about the 4th well? Well, there is a possibility of dealing with that. It can be a little tricky, frankly. What we do is a measurement we call cyclic exchange. We've got the 2 being probes 1 and 2, and well 1 and well 2 being wells 1 and 2, and they represent the 2 wells we're comparing. So in this mathematical situation here, we got probe 1 and well 1 plus probe 1 and well 2, and we had probe 2 and 1 minus probe 2 and well 2 together and divide by 2. That'll the value. Now it can be a little tricky. You'll have to think a little bit about how the play that goes, whether it's up or down from one versus the other, but you work that out. Okay, thermal loading. What is that? As you can imagine, you add a number of thermometers to your insert or lock that will increase the heat loss or heat gain if you're below ambient temperature. And the more that loss or gain that you have, that can create a shift in the temperature gradients in the insert. The controller will compensate for that. What's going to happen is it will re-zero itself to temperature that has been the set point. So there's a little bit of a shift, then the display is still going to read what that point was. So you can actually get is primarily that direct mode. We're just comparing the display and the under test. In a minute. This is a measurement now of how you can test that. And you can do that with the types of probes that you use. I've got a drill going along here at 421 or so degrees C. Our first probe we put in there is a value, and we're going to say that value is whatever the set point is. And then, of course, this point is going to stay the same, so the display is going to continue to read that same value during the entire process. I'm going to add here a second probe, which is live. We're measuring that, or plotting the data, as you can see here. Then I've got two more probes where they're just going to be for purposes of loading the block. They're rack probes, but we're not measuring them. See that as that second probe in, my thermometer dropped a little bit in temperature. And third thermometer drops some more. And we're still measuring the same first thermometer we put in there, probe 1. But he put another thermometer in there, the temperature drops. Display says it's right where it was before. It hasn't changed. Statically increases your uncertainty with the number of probes you put in there, and that could vary depending on the probes that you have and the block drywall and so forth that you're working with. Any other probes are in there? Are they looking the same, or are they a little different? Well, again, the difference between those two probes, and you look at this scale, you can see it's pretty small. You take an average over the highest, what appears to be the highest temperature and the lowest temperature. In this case, we've got 2 milligrees. Why? Well, as many of you realize, a 2-degree error is basically noise that's generated from moving that block in and out. The reuse 2 thermometers in the testing is to eliminate the impact of that kind of noise in the gradient measurement. We've got a little bit of it with this. You can see that even if the test goes on, it doesn't come back to where it was before. But the case is we're only talking about 2 milligrees. So each subsequent probe you pair, you might well expect that change relative to the reference probe. So if you use the indirect method, where we're using a separate thermometer and readout for your counting temperature indication, your error with a indirect mode is considerably less than it is with your direct mode. The next item to look at is control sensor hysteresis. Phenomenon you may or may not be aware of is that if you have say you have a thermometer in your dry well that has no whatsoever, and it's going to be this center line through the middle here. Now we're going to take your dry well from one temperature to the next as we go up, and then we'll go down again. As we go up, the temperature controller will react to the sensing element. Actually, by the time you get to the middle, you reach your maximum error. You go to the top, temperature, everything comes together, and as you go down in temperature again, you reach the middle of your excursion. You have an error in the opposite direction, and eventually it repeats itself every time you go up and down there. So what's going on? Temperature sensor in the dry well calibrator is designed such that it's an industrial sensor. What's industrial sensor? It's been built so that if that sensor is shocked in some way, it'll have less chance of shifting in temperature. So the windings, in the case of a wire-wound PRT, they are somewhat restrained, so that when that is, it will not shift nearly as drastically when it's dropped. You could expect some shift. It will not be drastic, and it will also exhibit some hysteresis. That's because the stress of the thermal expansion holding back some of that water, so that its resistance behaves in this fashion. So that be understood, you can go process of testing hysteresis going over a temperature range that you intend to use. Now notice, this is a different way of looking at the same kind of material. We're looking at a number of different temperature spans for that temperature sensor, and you can see that the deviation in the center varies, but increases with the span. Now these particular deviations are somewhat exaggerated. At the small deviation, the small span here, you probably wouldn't see anything. At least not with the sensors I've tested in our dry wells. The range. So how will you test for this hysteresis? You have to start with a reference thermometer that is of very high quality, that exhibits very little hysteresis. Given that, you'll cycle that dry well calibrator over the temperature range that you intend to use it. Your dry well says it is 35 degrees. That's pretty slow. We know that you can actually jump that up a little bit. But basically, you want to cover that range up and down, not just once, but multiple times. And what we'll find is that at each cycle, it varies a little bit. But after a while, the pattern will exhibit itself. And, when you do this, by the way, whatever temperatures you decide to dwell there, so it stabilizes, and you get a good average of that temperature at each point. Now, the minimum points will be at the bottom, top, and in the middle of that range. And scale that up and down at least 10 times, validate out, and you can see, take averages of the variations, particularly at this midpoint, that would anticipate there a hysteresis situation. Now, if you're using an external reference thermometer, and your external reference thermometer has little or no hysteresis, it won't be a problem. Early in stem conduction. As you might well imagine, most thermometers we have are in that you've got a temperature element in the above a sealed off tube, and you've got the temperature element there. It's attached to 3 or 4 wires, and lead wires going up to the handle where they attach to the internal cable that goes to your readout device. You've got a thermometer there, an element of some length, and you really need to understand what that length is and its general position in that tube. And the thermometer is going to be dependent upon the ability of the heat to come from the block into the thermometer. If this were a thermometer sitting here at the bottom, it's going to, we've got the top of a block here, and it's coming out the top of there. So you can well imagine that as you proceed down here, the temperature higher and higher and higher at this, in this case, is 420 C. And it will actually be 120 C. But where the problem is, there's a certain thermal resistance of the coming and being up to that thermometer, such that the temperature reaches the ideal of the same temperature as the temperature as the sensing element. Okay, here I've devised a block, and I wanted to eliminate the possibility of grids in block as or by the limitation of being able to control the various ports of that block to be at equal temperature. I mentioned before, in the case, if you've got a heat element at the same watt density throughout the length, the temperature increase till about the center where it's the highest. Well, what we try and do is compensate for that by using different heating element values throughout that block, equalize that out so it's as flat as possible. Well, that's something you can do in an approximate sense. So I built a block that was immersed into a salt bath, and you can imagine the salt bath was pretty uniform. I'm trying to evaluate then the effect of the thermometer as I try and do an axial gradient type of test. These happen to be all different designs, diameters, sensor lengths, and I've immersed them to the bottom of this 20 millimeter well, 20 rather, and I've withdrawn them in much the same fashion. So I'm every meter or so I'm taking a measurement. But what's happening here is, again, these sensors are different designs. They have different length diameters, different types of lead wires, that sort of thing. You can see that even though they're saying apparently the same temperature, the indication of temperature is varying. Okay, this is 20 meters depth. If you had a 6-inch block, that'd be about 150 millimeters, 1.5 centimeters depth, and you can see already the deviation between different sensor sizes and danes rather. We got a deviation, something on the order of 25 millimeters or 25 milligauge or so. Well, it's not too bad. What if the well is not quite so deep? Here's one that's 105 millimeters depth, not a tenth of a degree deviation, and for a 100 millimeter or 4-inch immersion depth, now we've got degree deviation, but in between different values. Very important. Men are going to be faced with the challenge of calibrating very short sensors. That's going to be a difficult challenge. You have to meet that the best you can. You want to try and do that with a temperature range which is very similarly designed to with your sensor length and diameter as your test, and insert those to the same depth. And again, center lines and do this you can, but your performance is going to be iffy because all of this is very difficult and impossible to predict. By comparison, this red thermometer here was immersed into the salt. So this red dashed line represents deviations. Again, we're drawing that just in the salt bath and see that conduction is negligible for a considerable distance up here. Now, if we were to magnify that further, you'd begin to see some of that even down to here. You need to have the set temperature immersed the top of the sensor. If it's immersed at least 100 millimeters, then most of that will be a non-issue. But the deep start to increase rapidly as that top of that sensor approaches the top of the fluid level. In this case, we've got a block constructed so that it's sealed. There's none of the fluid from the bath gets into it, so it looks like a dry well. It's completely dry, and we're seeing this kind of a problem with the dry well, and so that's a challenge with the dry well. You can do your work if you immerse it all the way to the bottom. Now, what do you put as a value for stem conduction? Well, there's going to be some estimating involved in that, and you might have to do something similar to this. It's very difficult, however, to separate stem conduction from grid, so you might end up having to kind of combine those two values. Ultimately, now we've come to the point to where we do some evaluation, and you'll have some form of an uncertainty budget. I wanted to, in this particular uncertainty budget, compare direct mode and indirect mode. So this is the direct mode. Again, that's the situation where you've got a is in fact the calibrated thermometer. You're using the control sensor as the reference sensing element, and temperature on the display. As we went through the previous information and testing, we said loading and his is subject to that direct mode. Now, there's other issues involved as well. The uncertainties with the reference thermometer and so on are not good. But if we do our evaluation here, we estimate our distribution. By the way, probably the distribution you have if you're using 2 sigma versus some minimum spread type of thing, it will come out in the selection of what distribution you're going to have. Is typical for 2 sigma. Anyway, different values in here for those particular quiz on look and cases, and the expanded uncertainty, we've got a value of 0.438. If we compare that thing, basically eliminating most of the therming by using the indirect mode, and hysteresis is not a function of the dry well here at all, then greatly improve our combined expanded uncertainty. So we can evaluate the thermal properties that are inherent in dry wells by this thing. We can come up with values that we can apply to our. We don't guess. We don't have to go by the uncertainties listed by the manufacturer, which may vary depending on the conditions. Making an estimate of uncertainty through analysis. Different modes can be evaluated, and the all effect is we can, just careful testing and analysis, we can improve accuracy of the calibration for our cases. Now it up to questions.
Okay, thanks, Mike, for that presentation. We're going to take questions. We've already received several, and we'll start going through those and answer as many as we can in the time remaining. So, Mike, let's go to our first question here. It's, how long can the probe be? If some part of the probe goes to the block, should I cover it to avoid temperature loss?
I've done comparisons. It does tend to eliminate some of the effect, but you need to keep in mind that the bulk temperature loss is going to happen a very short distance out well. You'll have the idea that if you've like a H probe in a 6-inch well, you're setting yourself to greater stem conduction. That's just not true. You've got some space out of that dry well before it reaches the handle in order to prevent damage to those connections. By the time you get out any reasonable distance in order to do that, this is there. So you can't improve by shorter select a thermometer on your overall general use and not make it short for a dry well calibration, because it will not help. Side of some kind of insulation, well, what kind of insulation would you use? If you're making measurements that are fairly high in temperature, you kind of restrict to fiber and fiber ceramic insulations. Fiber and bits of material can fall off if under the well and wedges itself, but a thermometer and the wall can stick a thermometer in there to where you have a really tough time getting it out. The big problem if you got an expensive reference thermometer or customer's thermometer that you're responsible for. So be cautious.
Okay. The next question, if I'm doing a calibration and verification of a dry well, should I consider the stability uncertainty and the uncertainty budget?
I would. I'd always do my own testing and evaluate the stability along with everything else. Certainly with our products, the stability specified is a larger than you may in fact find. So you can, by doing an evaluation of that, you can improve your uncertainty.
This is, do the reference and gradient probe move together? You know, that one example.
Reference probe always stays at the same location. Its purpose is to basically measure stability effects. Well, what I mean by that is when you've got a dry well, the stability is one thing, but every time you move anything, you get kind of a bump. What happens is you get variations in the thermal conductivity. It may resettle with the contact points inside the well, some little bumps and stuff. Looking for gradient measurement is simply what the gradient is. We don't want to worry about all those. The process of having a reference probe in there and then seeing the difference in the values basically eliminates the most of the instability as a result of those kinds of things.
If you have a 9-bore insert, should you test every hole or bore for radial testing?
Bores are, you have a specific insert which is, you've got all the holes the same size. Most of them are different sizes. It makes it impossible to different wells. So you're just going to have to make an estimate on what the impact is with the different sizes. That's standardized to 4 wells, all the same size. In wells, you would probably have to measure them all. Those are the closest, would probably be pretty similar. And extremes are going to be more extremes in looking. So I might go every other one, but certainly as you move away from ambient temperature to get to the higher temperatures, the likelihood of some great deviation increases. So I have to do a little experimentation once or twice to see how that stacks up. But generally speaking, those are pretty close if you've got 9 bores, and the impact from one to the next might not be a concern. I would certainly do it once or twice just to make sure that I was on board. And as I went back from time to time to recheck things, my foot got down a little bit.
The question is, what kind of frequency of axial, radial, and load testing would you recommend?
Well, kinds of things don't change a whole lot, so you might want to do it every 6 months, every year. When load testing, it's really more dependent on the kinds of probes that you're inserting in there. Yeah, they're essentially the same thing from one to the next, then you wouldn't need to do that very often. Again, you probably want to do some of your own hysteresis. Do this once every 6 months and people log and see if there's any variation. They happen. The welds and the insert could oxidize and create some issues there. Might have other might heat damage and other things that could occur over time. Good idea to check it once in a while in any of these, gradient and loading. But as far as loading concern, is the most significant factor is what's the diameter of the probe. If the same all the time, maybe not so much. With each different type of probably have to reevaluate, especially if it were significantly different. If you were making probes, all of a sudden you jump to 3/8-inch probes, and there's a big difference there, and you'd want to evaluate that. And that's primarily required if you were using which are dry well itself as your read and temperature reference. If you're using an external reference, then the loading isn't that much of a problem. You wouldn't have to do that so often.
Okay. Next question, Mike, is related to uncertainty budget. What's the difference between type A and type B uncertainties, and which also related to that is, do you need to consider a sensitivity coefficient? Type A and type B uncertainties.
Type A, type B. I'm going to be able to answer that properly. Obviously, an organization could handle that better. So rather than give you some on what that is, I'm going to have to pass on that one. As far as a sensitivity coefficient, I'm not sure what you mean by that. Maybe and that idea a little bit.
The thing I'll mention about the uncertainty budgets, we do have another webinar where we cover that that's been recorded. And if you go to our website on the on-demand webinars, you'll find a good chat out there on how you account for the different uncertainty budgets, in your uncertainty budgets. Go to the next question then, Mike, related to the immersion depth. Difference in immersion depth between the probe and then the gray probes. These when you're testing these probes, maybe you could review that.
The reference probe again is the same depth and location at the measurement, whether they're axial or whether they're radial measurements. We'll typically insert that to the bottom of the well, and then the grade probes will move from well to well. And the gradient probe for radial is basically the same probe, same kind of probe as your reference probe. But axial gradient, we go to the C13 definition, where the sensitive element must be 5 millimeters or less, and the diameter 6 millimeters or less. So that again moves up in 20 millimeter increments to cover your working area. And hopefully I've answered that question.
The next one, Mike, is there's always a difference between the reference probe value and the display, the hydraulic display.
It's going to depend on the dry block display is counted factory or you're able to do it a little bit yourself, and to be representative of the type of probe that was used to calibrate it. I've got the time and also the precision of the circuitry involved. If an external, it's got its own history. It's got its own sets of electronics with calibration history. Inevitably, they'll be somewhat different. If they're significantly different, you would want to investigate that to see which one's right. I've heard the story about the man with two watches. He knew what time it was as long as he had one watch. When he compared to a second watch, then he wasn't sure. Well, sometimes you have to get a third opinion in there to double check it. But some differences between the values, again, for the various reasons. They use a different type of thermometer with external readout. There was some differences due to the uncertainties that we've discussed here.
The next is to minimize axial uniformity related errors. I got the impression you don't recommend immersion and the reference probe to the maximum depth possible in the dry well. Is it correct, or did I misunderstand?
Speaking, you'll want to get them to the maximum depth to eliminate as much stem conduction as you can. And it's certainly more convenient. And everything the lengths of sensors is where you might want to consider sending them to different depths. That will help minimize some of the error related to axial gradients and sensor size. So in that case, I would carefully calculate where the center lines are of your sensors and try to insert them so center lines are lined up. Of their design being essentially the same, the sensor length being the same, I would insert them all the way to the bottom. But in this case, you got different sensor lengths, different design parameters. Then it's time to consider adjusting those immersion depths.
Next question, Mike, is about if a probe is linked to a measurement process, what effect would that have in the when you're calibration on it?
When a probe is connected to a measurement process, I presume that you mean that you're reading the value of this probe on some display that's part of the measurement process. In that case, you're going to have to make some offset based on what the value is. So if your reference says it's 100 degrees, your process says 3 degrees, just have to decide what kind of adjustment you're going to have to make. Generally, you make an adjustment to the process so that you make the correction in that device, whatever that readout is. So you do set. Could potentially be different. So I'm not sure I'm properly answering it, but not I'm familiar with. That's generally what you would do.